Hello everybody, I'm Michelle Maharbiz.
And I'm Vivek Subramanian. Let's get started. Today we are going to talk about nodal analysis. Nodal analysis is the first real circuit analysis technique that we're going to teach you. This is a technique that's fundamentally based on KCLs, which you've already learned about. Now, to get started, the first thing we need to do is we need to talk about the concept of a reference node. Let's consider a circuit such as the one shown here. You'll notice that the circuit has multiple resistors and a voltage source. Well, the voltage source is, of course, always defines a voltage with respect to its two terminals. But if we talk about the voltage at some particular node, let's arbitrarily say I was talking about the voltage at this node, what am I defining it in terms of? Because voltage is, of course, potential difference, so I need to talk about the relationship between this voltage and something else. What we do to simplify our analysis is we always start by defining a reference node, and that reference node will be what we use to discuss all other voltages relative to.
Okay.
And so commonly what we'll do with a reference node is we will pick a node. We'll tell you some rules to pick a node later, and we will call that 0. So we will arbitrarily, in this case, pick a node. Turns out it's not that arbitrary. There's reasons we picked this node. And we'll call it ground. Now, I showed a ground connection. That may actually not be physically connected to earth ground. But we call it at 0 because then when we talk about any other voltage, it's referenced relative to 0. So the math just gets easier to deal with.
Okay, so, this is one of the things that confused me as a student. People call this ground or earth, and it must have some connection to whatever ground really is, V ground. But in this case, when we're doing this math, it really almost has nothing to do with it. I mean, we're not implying that this is connected to a piece of ground or anything special. We're just mathematically saying that all the other voltages are referenced to this one voltage, and it's just become common usage to call that thing ground. Essentially, we are pretending that the potential at that node is 0.
That's correct.
Okay.
That's correct. All we want is we want to be subtracting 0 from everything, because subtracting 0 means we don't actually have to do any real subtraction.
And I guess historically it's called ground, as I think we talked about in the very first lecture, because many circuits, the universal reference is essentially earth ground, which has a very large supply of electrons.
That's right. That's why it was originally called ground. Of course, in a portable device,
right.
There's not a connection to ground.
Got it. Okay, let's go.
Now, why is that important? Let's consider two nodes. We have a node J and a node K, seen over here. And the voltage at node J is Vj, and the voltage at node K is Vk. What is that voltage in reference to? Well, given that I said it's defined with respect to 0, so Vj is actually Vj to ground, and Vk is Vk to ground. Since it's at 0, we just call it Vj and Vk. Now, if I wanted to know the voltage, for example, across the resistor, so the voltage between J and K, it is effectively, we call that Vjk, but that is just Vj to ground minus Vk to ground. Because we are referencing everything relative to 0, the math gets really easy.
Okay, so let me go through this again, because I think this clarifies something that arises. So we've told all of you guys out there that a voltage is a two-terminal property, right? It's a differential. And so sometimes people say, oh, Vj is 3 volts. But really what you're saying is once you define ground, when people say Vj is 3 volts, they really mean the potential difference between the node J and ground is 3 volts. It's always implicit that it's that node minus ground.
That's right.
Okay.
That's right. And by the way, this gives us a hint, therefore. It is often convenient when you're picking this, what we've so far said we've picked arbitrarily a node as ground, you'll often tend to pick whatever is connected to the negative terminal of your source.
Okay.
So in this case, I happen to have picked this as ground for good reason, because it's the negative of my voltage source. There turns out there's also an additional benefit because there's multiple branches connected to it. By calling this one 0, I eliminated a lot of terms from my equation.
Right, and we'll see that in a minute, I think.
That's right.
Okay.
So in other words, what we've basically been able to do is by defining everything with respect to the 0 potential, the math gets easier because now we can just talk in terms of VJs as opposed to talking in terms of VJ ground. And similarly, now when we talk about VJK, we'll just do VJ minus VK instead of doing VJ minus some other non-ground reference minus VK plus some other non-ground reference.
I got it. Okay, that makes perfect sense. So VJK is really just VJ minus VK.
That's right. Now let's move on and let's actually start taking the next steps into forming a nodal analysis framework.
All right, so what we're about to go into is essentially an algorithm for taking a circuit like the one that's shown here and arriving at a set of equations with a set of unknowns that you can solve for that will tell you everything you need to know about that circuit's currents and voltages. Okay? So let's take this circuit as a working example, and I'm going to just give you steps that you will do. Now, I want to point out here, and I think it's useful, if you get good at applying these steps at the beginning as you practice, you can't go wrong except with a little bit of arithmetic, making math mistakes. And computers have been following these steps for decades. It's that simple. It's a very, very nicely structured algorithm. Okay, so first of all, let's look at the circuit. We've got independent voltage source V0. We've got an independent current source I0. That's I0 positive pointing down. We've got some nodes. We've labeled them here V1, V2. And we've labeled for you currents through all of these little branches and give them the numbers. All of this is arbitrary. These arrows are arbitrary and so on. They're just there to label them, and we're going to make use of those labels. Okay? And the numbers are all arbitrary, obviously. So the first step is you're going to identify all the extraordinary nodes.
As a reminder, extraordinary nodes are nodes that have 3 or more branches.
That's right. And so what's a counterexample? Well, this is an ordinary node. It has only 2 branches connected to it. But here's an extraordinary node. Here's another one. It's got 1, 2, 3 branches. Here's another one, 1, 2, 3. And here's one with 3 as well. Okay, so we've got 4 extraordinary nodes. Now we're going to pick one as ground. Okay? Now I'm going to blindly do what Vivek told me to do, which is pick the one connected to the negative terminal of the independent voltage source. And that's a pretty good rule. If you're asking, which one should you pick given some random circuit? Well, what I always do is I find the independent voltage source with the most number of connections on its negative terminal, most number of branches on that node, and I put ground on that.
So in this circuit, it seemed pretty straightforward because you only had one voltage source. Mm-hmm. So you picked the negative of that voltage source to be ground. What would you do if you had 2 or 3 voltage sources?
So I would first go to the rule I just mentioned. I try to find one source that has more branches on its negative terminal node than the others, because that's going to simplify my equations. But let's say I don't do that. It'll still work out. This will work. And in fact, let's say that I don't follow any of these rules. Let's say I put ground up here. I'm still going to be able to solve this circuit.
Yeah, your equations will just be a little bit more cumbersome, but you'll be able to solve them.
But the answer will be the same, and you will get the right answer. So you don't have to worry that you might put ground in the wrong place that will give you a wrong mathematical answer. That's not true. We're giving you these rules because it just so happens that there's, it'll simplify the equations. It'll make your life easier. But if you're doing this, for example, with, a Wolfram alpha or a calculator, you're going to get the right answer even if you put, ground here, for example. Okay? Fair enough?
That works.
Okay. So anyway, we put it there, and so now V4 is identically equal to 0. We're saying that the potential here is 0. Okay. Now we're going to assign node voltages to all the other ones. Okay. So V1, V2, and V3. All right. So that's node 1, node 2, and node 3. They're going to have those numbers and those names. And now it gets pretty straightforward. All we're going to do, once we've picked one as ground and the other ones have numbers, 1, 2, 3, A, B, C, we're going to apply KCL to each one of them on their own. So we're going to start with this node, and we're going to do KCL around this node. When I do this, I'm going to get an equation. Okay? Then I'm just going to write that equation somewhere. Then I'm going to move on to the next one, apply KCL. I'm going to get another equation. I'm going to go to the next one, apply KCL. I'm going to get another equation. Each of these KCL operations is independent of the others. I'm just sitting there sort of blindly writing KCL for that node, okay, with whatever little labels I created for my KCL currents. You could call these anything, all right? And when I'm done, I'm going to have a bunch of equations that I can solve for. So let's start. Node 1. Well, node 1, just by inspection, is obviously I1 plus I2 plus I3 must equal 0. That's all the currents exiting the node must equal 0.
And that you had positive signs there because you picked them all going away from the node.
That's right. That's right. I sort of skipped over that, but you're absolutely right. Because I drew the arrows on purpose to be away, I can do this plus this equals 0. And you should get used to doing that. It's just faster. If I flipped I3 around and I decided to make the arrow pointing left, I could have written I3 equals I1 plus I2 and gotten the right answer, but that just leads to confusion. I think you get used to drawing all your little KCL currents going out, you can just write I1, I2, I3 equals 0. And now here's the whole trick to Nodal. Once you write this, and in reality, in about 2 slides, you'll probably skip doing this step altogether. But once you write this, I can now, from the node voltages, substitute in expressions for those currents. So let's look at I1. Well, I1 is the current through this resistor R1. And what's the current through this resistor R1? By Ohm's law, it must be the voltage across the resistor divided by the resistance. Well, the voltage across the resistor is V1, because we know that that's the voltage of this versus ground, minus this voltage, which coincidentally, nicely, happens to equal 0. So it's just V1, right? V1 minus 0 divided by R1. That's the current.
And here you see the example of why picking the ground that way made our life a little easier in terms of the equations.
Right, because that's exactly right, because there's nothing there. It's just V1. Let's look at the I2 so you can kind of further see what Vivek is saying. So in case of I2, what is the current I2? Well, it's V1, right, minus this voltage here, V0. That's going to be the voltage at this point where my arrow, my pointer is, divided by the total resistance between them, which is just R2 plus R3. So think about it. Let's say I just join these together into one equivalent resistor. I just did that in my head, right? That's going to be R2 plus R3. And so the voltage across that resistor divided by the resistance gives me the current. And so what's the voltage across this combined resistor? It's V1 minus V0. Okay, so I get this expression. And then I3, well, I3 is just the current I3 is just the voltage across resistor R4 divided by R4. So what is that? It's V1 minus V2 gives me the voltage across this. And remember, the current's pointing to the right, so it's V1 minus V2, because there would be a plus here and a minus there for the resistance voltage, right? Divided by R4. And that equals 0. All right, so you basically can see the form of this. What you're going to end up with is an equation where the node voltages are the unknowns. You see, we know all the R's. We're solving for the V's. And we have 1, 2, 3 voltages, so we better have 3 equations. And that's why we're going to do KCL at these 3 nodes.
Another good thing to remember is when you're writing your equations, a good way to keep track of terms and make sure you haven't skipped any terms is if you see 3 branches, you better have 3 terms, one associated with each branch.
That's right. That's exactly right. So let's do another one, and then I want to, after I do all 3 of them, I'm going to point out one common mistake that is often done. So let's look at node 2. So node 2, I'm going to even skip writing this expression here. We know it's going to be I4 plus I5 plus I6 equals 0. Now we just want to fit in expressions for each of them. So what's I4? Now I4, notice the current is pointing to the left. So by Ohm's law, the current going left on the resistor times the resistor is going to equal the voltage on the resistor where the positive terminal of that voltage is here, plus, minus, where my arrow is, plus on the right, minus on the left, right? That's the passive sign convention in Ohm's law. So that tells me that this current I4 is V2 minus V1 divided by R4. And that makes a little bit of, if you want to skip ahead, it makes a little bit of sense as a check, because I4 should be the negative of I3, right? You see they're pointing the wrong way. They should be the same value, but I4 is the opposite polarity of I3. And if you look here, this is V1 minus V2 over R4, and this is V2 minus V1 over R4. It's just a negative sign. We're good. Okay, so I5. Well, what's I5? Just by observation, that's pretty easy. This source forces I5 to be minus I0, right? Because the source is pointing down. I5 happens to be pointing up. I0 and I5 better be the same magnitude, and just the sign that's flipped. So that's minus I0. And what's I6? Well, now we're getting good at this. I6 is just V2 minus V3 divided by R6, and we're done. And node 3, I'm going to go through it real quick. And actually, you know what I want to do? I'm going to give you 2 seconds to go through each of these. It's going to be I7 plus I8 plus I9 equals 0. So this is I7, this is I8, and this is I9. Take a second. I'm going to be quiet, and then I'll just walk through it. Okay. So let's go through the first term, I7. Well, I7 is just V3 minus, what voltage is on here? 0, divided by R5. Very similar to when we were doing this R1 here. What's I8? It's V3 minus V2 divided by R6. And again, I8 is the negative of I6. And so you, in fact, get exactly what you expect. This is the negative of that. and plus I0. And so why is that? Because I9 points up, goes over, and identically is exactly the same as this independent source current, which is I0. Okay, so the one thing that I wanted to point out, and I sort of already skipped to this and said it, but I find that sometimes students get these flipped. So for example, in the node 1 equation, when they're writing I3, they'll write V2 minus V1 over R4. Sometimes this is just carelessness. You know, you're going fast and you get it flipped in your head. But sometimes it's conceptual. And they don't realize that because of Ohm's law and the passive sign convention, the expression is V1 minus V2 divided by R4 because the current is going from left to right. So the plus, the first term is on the left and the other one's on the right.
So the simple way to think about that is to get the equations written right for in a KCL. The first voltage, the one that you're subtracting from, is where your arrow starts from. The second voltage, the one you are subtracting, is where your arrow ends.
Perfect. That's exactly right. Okay, so what's the last step? Well, that's just solving. So look, we've got one equation in 3 unknowns, V0, V1, V2, and we've got another one here. Actually, sorry, V1, V2, V3, because V0 is known. And here's the second equation, and here's the third equation. And so you can solve this however you want, right? If we're doing this by hand, and it's useful to see this and to do it the first few times, you're going to factor out for each equation, you're going to factor out the terms such that you have a prefix to V1 minus something times V2, and then V3, of course there isn't anything here, equals, and then this is going to come from your sources, V0, in this case R2 over R3. So this is the first equation. The second equation, if you factor the V1s, V2s, and V3s, you're going to get something times V1, something times V2, something times V3, equals, and this comes from a source. And likewise for the third one, there happens to be no V1, so you got V2 and V3.
So the key point is, remember that in these equations, the V0 and I0 are known. Those are values that are known. So what you've ended up with are 3 equations with 3 unknowns at the most.
Right. And this is something that we'll come to later. We're not going to do it in this lecture set. But notice that all the resistors are on the left side with the unknown voltages, and all the source terms are on the right side. So it's something to notice. It's not a coincidence. But once you do this, you know, you should all of you should be familiar with linear algebra, and you can see that the form of this system is 3 equations and 3 unknowns. This is a matrix, and you can use linear algebra to solve for V1, V2, and V3. You could, of course, do it by elimination, like you do when you're first learning this in junior high, which is to one by one reduce these equations, but solve it however you want. When you're done, you're going to have your answer.
Okay, so you've now worked through your first nodal analysis problem. What we're going to do now for the remainder of this section is we're going to introduce some slight complications, and we'll tell you how to deal with them. And the first one we're going to deal with is a circuit where you happen to have what we'll call a floating source. So what is a floating source? Well, let's look at the circuit over here. It has 2 voltage sources. We cannot label both as ground. We can only have one reference. So what are we going to pick? Well, Michelle, which one would you pick?
Well, I'd pick VS1.
And you take the negative of VS1?
Right, because the negative of VS1 is connected to all of those branches, and that's just going to make my life real easy, right? Because every one of those KCLs I'm going to do at the upper nodes will end up with 0. You know, it's going to be, for example, this node here minus 0 divided by R1 for this current, and so on. And so the more of these I have, the better my life is.
That's right. And the other way to think about it is you don't have to write a KCL with
with
all of these different terms down at the bottom. So that's right. So you'll pick one. And it just in this case, we've picked the negative of VS1 as our ground. Now what that means is we get to simplify our equations with respect to various terms, but we have to figure out what we want to do with this other voltage source. This other voltage source turns out to be somewhat interesting to deal with for a simple reason. When we are trying to write KCLs, how are we going to figure out the current? So let's say I wanted to do the KCL at node A or node B. Let's take node A as an example. Well, I want to know the current that's coming along this branch that has R6 and VS2. That's difficult.
Well, I don't know the current through VS2 is what you're saying.
That's right. We don't know the current through VS2.
All right, so there's probably some little trick, so to speak, we can do to deal with any time that there is an independent or dependent, actually, voltage source stuck in between my nodes.
That's right.
Okay.
And the technique we're going to introduce to do that is something called a supernode. So the way we're going to deal with this is we are essentially going to recognize something kind of interesting about a floating source. So let's take this floating source, and let's look at what happens at each terminal. Okay? So I'm going to call the current through the floating source IS. I don't know what the current is, but there is some current IS through the floating source. Let's look at the positive terminal of the floating source, and let's write a KCL over there. So if we write a KCL at the positive terminal, we have a current I1 plus I2 plus I3 plus IS is equal to 0. Okay. So the current through R5, which is I1, the current through R3 and R4, which is I2, the current through R2, which is I3, and the current through the source, we've designated them as all going away from the node. So we can then write I1 plus I2 plus I3 plus IS is equal to 0. Now, we don't know what IS is, but let's leave that alone for now. Now, let's do it at the negative terminal of that source. At the negative terminal at the source, we have I4, the current going through the resistor R6, minus IS, and it's a minus sign because we want our arrows to be pointing away from the node, whereas IS points into the node. So we've got I4 minus IS is equal to 0. Now, look at those two equations. The first equation has a positive IS. The second equation has a negative IS. If we were to add them, it would disappear. So then what we can write is I1 plus I2 plus I3 plus I4 is equal to 0, and the IS disappeared out of the equation.
Wait, but this is, all you're doing is what we talked about when we were first talking about KCL. You're just saying that KCL around that dashed oval on the circuit holds.
That's right. And in fact, that's exactly correct. But I'm using it now to deal with a floating source. Right. So effectively what I'm going to do is that dashed oval becomes, I treat it as a node, and I don't worry about the fact that there's a voltage source inside. So what we've done is we've basically now said, we're never going to deal with floating sources like this. We'll just draw a box around them. We'll write a KCL on the outside of the box. And then we'll somehow deal with what's going on inside the box through a separate equation. And this is what we call a supernode.
All right, so let's look at this idea you just introduced us to in the context of another circuit. So you're saying a supernode is formed whenever there's a voltage source connecting two extraordinary nodes. That's a formal way to look at it. So if I look here, I've got V2, V3. Both of these are extraordinary nodes. They've got 3 branches. But, you know, my professor here snuck in this voltage source here to make my life difficult. But this is going to become a supernode. And I guess I see another one here because there's an extraordinary node there, an extraordinary node there, and I've got a voltage source stuck between them. I also notice in this case there's a resistor also in parallel. I guess we'll come back to that. But the basic definition is this. Okay? And we don't know what the current between V2 and V3 is. This is what we were just talking about. There's no way to really solve for this, write an expression for this independently as we were doing with the basic nodal example. But the good news is, once you get good at doing this, there'll just be less nodes overall, less equations, because we're going to treat this whole blue thing as one node, and life is going to be great. And the other thing I'll say is, we're not going to treat the source to ground in a supernode. There's really no reason to do that. So in this case, you know, technically you could make some argument about wanting to do some sort of supernode with this here, but there's really no reason to do it because we've defined this ground, and so we know V1 is identically equal to, say, 20 volts in this case. We know V1 is 20 volts by the mere definition of where the ground is. And then once we do that, we're going to designate all the other supernodes, and we're going to follow this little rule we're about to give you.
So there's an important point to note here. If you notice supernode A, well, that's exactly what we had looked at earlier, where you just have a voltage source. But if you look at supernode B also has a resistor in parallel. And that's okay, because if you look at that box, the dashed box drawn all the way around, the KCL still has to apply. So we can include a resistor inside our supernode definition, and it's not going to cause a problem.
That's right. That's right. And you'll see this by exercise, really, that this R4 doesn't really cause any problem at all. So what we're going to do is 2 steps. The first thing you can do, and you can actually do this in any order you want, but let's start with the first step. You're going to write the KVL equation for the supernode. So in most cases, it's actually pretty easy to do. What do I mean by that? It's the simple observation that, in this case, take supernode A, V3 minus V2 equals 10 volts. Right? So that tells us something about the internal working of the supernode. In this case, V4 minus V5, now notice there's a resistor here, so V5 isn't ground. So V4 minus V5 is 16 volts.
And by the way, this is why you could get to include that resistor in there. The presence of the resistor in there, namely a resistor in parallel with a voltage source, does not mess with your ability to develop a KVL.
Oh, I see what you're saying. Because basically what you're saying is V4 minus V5 will always be 16 volts because of this source. This resistor can't change that.
Exactly.
Oh, at best, all it's doing is drawing some current down it coming from here, which really doesn't affect our equation.
Exactly, because within the supernode, we're only doing a KVL.
There you go. Well, that makes sense. And then we've got to write KCL. So now we're going to treat this. Once we've written this KVL, we set it aside. It'll become useful in a minute. And what we're going to do is just write KCL for the whole supernode. And this is really easy. It seems weird at first, but in fact, it makes these problems go really fast. So let's just do this in our heads real quick. What's the KCL for the supernode? It's this current. Let's say I drew it pointing to the left. It's the current through R4 going from V2 to V1, plus the current through R3 going from V2 to ground, plus the current from V3 down to V5, so V3 minus V5 over R5, plus the current from V3 to V4 through R4. Those are 4 branches that are connected to the supernode. Those 4 currents must equal 0, and that's it. That's the KCL for this supernode. You don't have to do anything else. You don't have to worry about what currents are going inside the supernode. That's the trick. Okay? So rather than go and do the same thing for supernode B, you're welcome to pause here and do it for yourself. We're actually going to do a couple of quick examples, and Vivek will walk you through them.
Okay. So let's go ahead and take a portion of a circuit. I haven't got the whole circuit shown, but I've got part of a circuit shown. And you see this circuit appears to have a supernode within it. And we see it's got a 10-volt floating source. And we see that it has a node on the negative side, which we call V2, and a node on the positive side that we call V3. And we've defined some currents, I1, I2, I3, I4, I5, and I6. Now, our supernode definition said we would just draw a box to encompass the source, the floating source. And we'll not worry about the floating source anymore. And we will basically write a KCL then around that box. And so around the box then, we no longer have to worry about I3 and I4, and instead the KCL simplifies down to being I1 plus I2 plus I5 plus I6 is equal to 0. In other words, I took a box around the floating source, and I wrote the KCL for the terminals, for the branches coming out of the box. And then I have an auxiliary equation, which is my KVL equation for what's happening within the supernode. And that, in this case, is pretty straightforward. Well, look at my supernode. It has V3 on one side and V2 on the other. And because I have a voltage source in between, I know that the voltage difference between those is 10 volts. So I've got V3 minus V2 is equal to 10 volts. So you see the benefit of this. The internal currents within the supernode, namely I3 and I4, canceled out. And so I didn't have to worry about those, and I've now got to simpler equations with less terms.
Okay, and one thing I want to clarify, the reason you did V3 minus V2 equals 10 volts is simply because the plus part of that independent source is on V3. So
correct.
Otherwise, it would be V2 minus V3 would equal negative 10 volts.
That's right.
Okay.
It's because the voltage source is positioned with a positive towards V3.
Okay.
Okay, so that's that simple case. Now let's throw that into something just like that, and let's throw it into an example. And in this example, again, we see that we have a voltage source. We also have a current source here, and we have a floating voltage source. So this is a good candidate then for a supernode analysis. And let's say what I want to do is I want to determine V1 and V2. So let's go ahead and set this up. So we'll define our supernode. And for our supernode, we can then write a KCL, which is I1 plus I2 plus I3 plus I4 is equal to 0. Let's take them one at a time very quickly. I1 is going to be V1 minus 4 divided by 2, the current through the 2 ohm resistor. I2 is going to be V1 divided by 4, the current through the 4 ohm resistor. I3 is going to be V2 divided by 8, that's the current through the 8 ohm resistor. And I4 is going to be minus 2 because it's the opposite direction of the current source. In other words, going out versus the current source going in. And we'll say that's equal to 0. Now, we can simplify that equation out, so just straight algebra, and we get 6V1 plus V2 is equal to 32.
Wait, but, okay, so now we did nodal, and we've got one equation and two unknowns.
That's
we
right.
Can't solve that.
We could not solve that. We need something else. Well, you remember when we introduced the idea of the supernode, we said there's a second part to the problem.
Oh, that's right, the KVL.
That's right. So we get to do the KVL, and remember the KVL equation for the supernode. We've got an 18-volt floating source, so the KVL equation says V2 minus V1 is equal to 18 because the 18-volt source is connected with its positive at V2 and its negative at V1. So V2 minus V1 is equal to 18. Now we have two unknowns and two equations, so we can solve, and the simultaneous solution says V1 is equal to 2 and V2 is equal to 20.
Fantastic. Okay, so to summarize, we were given this circuit. We're going to apply nodal analysis to it. We chose our ground, which we put at the negative terminal of the battery, or the source. We had only two extraordinary nodes, V1 and V2, so we were following the rules. But then we go to write our KCL, and we go in, oh, there's a source stuck between our two extraordinary nodes, V1 and V2. And then we followed, for this example, our little supernode trick, which is to do KCL around that whole node together. And it turns out, obviously, because we wanted to do it that way, that's the whole problem. There's just one supernode in the whole problem. But this problem could have been connected to other things, and there might have been other normal extraordinary nodes and so on. Either way, we're doing nodal. Okay, I got it. Huh.
So this is the beauty of the supernode. It works extremely well.
Okay, so a couple of other things to really wrap this up. Is a few more slides. There's a couple of things we want to point out. There's some things we call trivial nodes, and trivial nodes is really any node with less than 3 elements is some sense trivial. I guess you could call these ordinary nodes, as we've been talking about them earlier. And basically, there's no point in labeling this as a separate nodal analysis node. Now, we already, strictly speaking, told you this. We said go identify extraordinary nodes and label them and don't label anything else. But just as a pointer, because you may do it by mistake when you're working through it, there really isn't any point in doing this. It's better to avoid writing equations for this and deal with them later as you're working through it, because they'll all fall out trivially. When you're writing the equation for this, for example, let's say I was doing KCL around this extraordinary node, which is the correct thing to do. The current coming out this way would just be this voltage minus this voltage, which happens to be ground, divided by R3 plus R4. There's no need to call this V something else, like V9 or something, and work out this and then work out that, because these things will always equal each other.
So if I understand you correctly, what you're saying is since in an ordinary node, it's just a series combination.
Yeah.
Well, you might as well just write the series combination directly rather than writing another KVL or KCL equation.
Right, because whatever current's going through R3 is going to go through R4. So
Right.
it's the same current. There's no point in doing separate equations and just making more equations for nothing. They're very easy.
Okay, and then the final thing to talk about in relation to this is dealing with dependent sources. So you'll recall when we introduced sources several modules ago, we talked about the idea of a dependent source, and that's a source whose voltage or current depends on some other parameter. Now here's an example of a voltage-controlled current source. So this is a source whose current is a function of some other voltage. And so in the particular example shown here, this is a current source whose current is a function of a voltage V2, which is measured in this case across some resistor R2. So it turns out, while it may initially worry you when you see a dependent source showing up in a circuit, it's actually not a problem to deal with. Basically, treat it exactly the same in terms of how you do your KVLs, KCLs, choice of supernodes, etc. Solve it exactly as you would, just, in this case, write your current as Ix, where Ix is equal to K times VR2, and everything will solve itself.
All right, so let me go through this in my head. So you're saying let's say I go write KCL for this node. I'm going to write this standard, I'm going to have to write 4 current equations. So one's going to be here, one's going to be here, one's going to be there. No problem. When I go do the 4th one, you're saying, I just say plus IX. So for example, this current I1 plus this current I2 plus this I3 plus IX equals 0, and then I just substitute this in.
That's right. Well, what I'm saying is, let's do it. Let's actually do it. We've got enough terms here to solve it.
Okay.
Okay, so let's do the KCL here to test. It's going to be VK minus VJ over R2 plus VK over R5 plus VK divided by R3 plus R4 minus IX.
Right, and that's because IX is pointing left and down, and so it's minus IX.
Correct, is equal to 0.
Now, but hold on. So now I have that equation, that's fine, but I don't know what IX is. I can substitute in K times VR2, but I don't know what VR2 is either.
That's, well, not yet. So we can substitute in K times VR2, but you do know what VR2 is, because VR2 is just the voltage between VJ and VK. It's defined as VJ minus VK in this example, because I've defined VR2 with the positive on VJ and the negative on VK.
Oh, so basically what you're saying is it's going to be pretty simple. Either there'll be a current there or a voltage, but those things will always be related to node voltages in the circuit.
That's right. So the point is, if you didn't have this last piece of information, you would feel like you've got more unknowns than you had equations when you wrote your KCL.
Right.
But because we have this one other piece of information, namely the information that defines the current control dependency, we have enough equations to solve our equations simultaneously.
That makes sense. And I think those of you at home, you know, with a little practice, you'll see that it falls out pretty easily.
Yeah, I think the key lesson we want to give you is, as far as dependent sources are concerned, they're no different in how you deal with them than regular independent sources.
But I'm a little suspicious. So that's for current sources, I see that. But why don't you tell me about dependent voltage sources? That seems a little bit like there would be. Well, okay. Well, maybe we should do a current-driven current source first.
Yeah. So
maybe I'm skipping ahead.
Well, a current-driven current. Well, actually, but this will also show you a similar problem. Because whether you were doing a voltage-controlled voltage source or a current-controlled current source, you'd have to figure out a current to determine a current, right? That's the issue that you have here. But again, it's not so difficult to deal with. So here's an example where I have a current-controlled current source, or a CCCS, and the current is defined as being the same current as is produced through this resistor R2.
Okay.
So if we were to do a KCL over here, what we would basically do is, let's do it at the node K. We would have, and let's say we're doing it for currents coming in, just to make life, or let's do it for currents going out. We'll have minus IR2, which is VK minus VJ over R2. And then we'll have the current coming down through the resistor, so that's VK divided by R5. We'll have the current through R3 and R4, which is VK divided by R3 plus R4, minus IX for the current coming out through the current source.
Okay.
Now, the problem there is you don't know what IX is. Well, if you substituted IX is equal to IR2 into this equation, you get part of the way there, but you don't know what IR2 is. Well, you kind of do, because IR2 is VJ minus VK divided by R2.
Okay. So the bottom line is they always depend on these node voltages one way or another.
That's right. Now, one thing we should point out is, in many cases, it's convenient to just directly substitute in the dependency when you write your KVLs and KCLs. So when I write my KVL and KCL, instead of writing this as IX, I can just write IR2.
Right. You're saying once they do this once or twice, they'll see that they can just substitute it indirectly and not have extra equations.
Exactly. It reduces the number of equations, but it's effectively trivial to deal with.
Okay. Oh, this is the one that I was worried about, dealing with dependent voltage sources. But I guess you've told me enough that I think I can figure it out. I guess in the end, you know, let's say here we've got this dependent voltage source. It's going to give us the same problem as an independent voltage source, in the sense that if it was, in this case it's connected to ground, but if it was you know, floating between two extraordinary nodes, we'd have to do a super node as well, right?
That's right, but that's fine. By the way, there's something important to note here. You'll notice that I picked ground on the dependent source.
Oh, that's right. But I guess the reason for that is you saw that there was just that many more branches off of this guy's negative terminal, so you just put the
That's
ground.
right. So those rules we told you for picking ground, they work whether you are talking about dependent sources or independent sources. pick a ground that makes your life easier. I picked this one because I have so many branches coming to that point.
Okay, okay. And then I see, right? I mean, whatever equations, are related to, say, this voltage source, I see that there's an unknown VR4. And again, as you said, I might worry, but I can immediately see that VR4 is just going to be the voltage across this. So it's pretty simple to write an equation around it.
That's right. And you can put these inside supernodes. You can do all the tricks that we've learned with independent sources. You can do with dependent sources.